So today we're going to unpack something called COM, a potential breakthrough in AI that could fundamentally change how our most advanced models work. It stands for Continuous Autoregressive Language Models, and it's aiming to solve one of the biggest, most fundamental problems in AI right now.
Okay, let's just dive right in with a question that I think a lot of us have had. Why do these massive, incredibly powerful models like GPT-4 or Gemini, why do they sometimes feel so slow? Well, the answer lies in this fundamental bottleneck, a kind of digital traffic jam that's happening deep inside their brains.
So here's our roadmap for this explainer. We're going to start by looking at that token traffic jam. Then we'll explore a new path forward using something called vectors. After that, we'll check out the brand new toolkit Calm had to invent, see how it actually performs, and finally, talk about what this all means for the future of AI.
So what exactly is this bottleneck? Well, it all comes down to how these models generate text. See, right now, every single major large language model works by predicting one tiny piece of a word, a token, at a time. Imagine trying to write a novel by thinking of just one letter at a time. I mean, you'd get there eventually, but it would be incredibly inefficient.
This really lays it out. On the left, you've got the old way. The model inches forward, then cat, then sat. This is what the researchers call low semantic bandwidth. But the Calm approach on the right, that's a superhighway. It predicts a whole chunk of meaning, a concept, a vector that represents the entire phrase the cat sat on, all in one single shot. Now that is high semantic bandwidth.
And to put this into perspective, each token that a massive multi-billion parameter model predicts carries a ridiculously tiny amount of information, just 15 to 18 bits. It's like we're using a supercomputer to take baby steps. And this right here is the core inefficiency that Calm is designed to fix.
Now you might be thinking, well, why not just make the tokens bigger? Have a token for every possible phrase. The problem is, the model's vocabulary, its dictionary of all possible tokens, would have to grow exponentially. We're talking about an impossibly huge number. It's just not computationally feasible. We need a much smarter way to do this.
And that smarter way is to completely change the game, to leave the world of discrete individual words behind and enter the world of continuous ideas, represented by these things called vectors. This is the real paradigm shift at the heart of Calm.
So how do they actually do it? Well, the key is a tool called an autoencoder. Think of it like a superpowered zip file for language. It can take a chunk of text, let's say 4 tokens, squeeze it down into a single, dense vector of numbers, and then, and this is the crucial part, unsqueeze it back into the original text with almost perfect 99.9% accuracy. Okay, so this shows how it all fits together. First, you take a chunk of text, like the cat sat, and you encode it into one of those vectors. Then, and this is the magic trick, the AI's job is no longer to predict the next tiny token. Its job is to predict the entire next vector. Finally, that predicted vector is decoded back into a whole new chunk of text. The model is now thinking and generating in meaningful leaps, not just tiny little steps. But here's the thing. When you're playing a brand new game like Predict the Vector, you can't use the old rulebook. The standard tools for training, for grading, for even controlling the AI, they just don't work anymore. You need a completely new toolkit.
And that's what the Calm framework introduces, 4 key innovations. To train the model, they use something called likelihood-free modeling. To grade its performance, a new metric called LLM. To control its output, a new sampling method. And underpinning all of it is the need to make that autoencoder incredibly robust.
Making this work isn't as simple as just grabbing any old compression tool. That autoencoder has to be seriously robust. And why is that? Well, because if you have a brittle one and the AI makes just a tiny, tiny error in predicting a vector, that error can explode into complete gibberish when it gets decoded. The whole system needs to be smooth and forgiving, not chaotic and brittle. Think about it. You can't possibly calculate the probability of something in an infinite space of ideas. It's impossible. So the old training methods are out. The solution is called likelihood-free modeling. Instead of asking, how likely is this answer? It asks, how close is my prediction to the right answer? It trains the AI by simply measuring the distance between its guess and the correct target vector. It's a really clever workaround that doesn't need probabilities at all. And if you can't use the old training methods, you can't use the old grading methods either. Standard metrics like perplexity just won't work. So they invented LLM. The best way to think about it is as a new kind of report card.
one that's designed for this new vector-based world. It rewards the model for making honest, well-calibrated predictions, and it allows for a true apples-to-apples comparison between Column M and traditional AIs.
All right, so we've got the new method, we've got the fancy new toolkit, but does any of it actually work? Let's look at the results and see how Calm really performs when you put it to the test. This table right here is pretty eye-opening. Now, the first thing you might notice is that the Calm model actually has more parameters than the baseline transformer. But then look at the columns on the right, the flops, which basically measure how much computer power you need. Calm is significantly cheaper, both to train and to run. And this bar chart just makes that difference crystal clear. To get roughly the same level of performance, the Calm model requires 44% less computation to train. That is a massive gain in efficiency. This isn't just some tiny tweak, it's a fundamental improvement in how much performance you get for your compute dollar. You know, the researchers themselves really sum it up perfectly here. Cal isn't just another option. It's pushing the entire frontier of what we thought was possible, giving us better performance at a much lower computational cost. And this brings us to what might be the biggest takeaway of all. This isn't really about just one new model. It points to a whole new direction for AI development. The future, it seems, might just be continuous. You know, if you look at the history of language models, there's this really clear evolution. We started way back with models that worked letter by letter. Then we graduated to the subword tokens that we all use today. This slide suggests that the next logical leap is to continuous vector models like Calm. Each step up is about increasing the amount of meaning the model can handle in a single thought. And this really is the big idea. For years, we've basically improved AI by scaling on two axes: more data and bigger models with more parameters. Calm introduces a revolutionary third axis to scale on: the information capacity of each individual step. This means instead of just making the model bigger, we can make each one of its thoughts more powerful, more meaningful. And this is the ultimate promise, isn't it? This new approach acts as a powerful new lever for efficiency. Pulling on this lever could be what unlocks the next order of magnitude in performance, making truly powerful AI more accessible, cheaper, and faster for everyone. Which leaves us with a final and pretty fascinating question to think about. For the last few years, the race has been all about building bigger and bigger and bigger models. But maybe, just maybe, the real path forward isn't about making them bigger, but about teaching them how to take much, much smarter steps.